Okay, thanks, Kirtan, and thanks, guys, for inviting me to give this talk. So you already gave a good introduction, so I'm not going to spend much more time on this. Just to say that I've treated this as like university type of invitation of talk. So I do focus quite a lot on the work that I did within this area. But on the publication that I mentioned, you will find there a lot of other reference for the literature. Okay, so this is the content of the talk. So the first two parts is really a very brief overview of where the SDN, the network virtualization, have started, and then really the aim of this talk is to go into the use of these two technologies into the telecommunications networks. So not so much, let's say, in the data centers where they were born, but really into the public network side. And then I will focus quite a lot on the work that we did on the point virtualization, which is really core for this. And then I wanted to also go a little bit more into this disaggregated optical layer. And at the end, I will introduce a new tool that we have developed called Minute and Optical. And then when I go to the conclusions, what is really trying to see what's coming next and what's important to focus on. I also will talk about DoubleNets, which is a new a new research testbed that we are developing here in Ireland. Okay, so software-defined networks. So what is software-defined networks? I mean, it all started with OpenFlow. And OpenFlow, it's something that allowed in practice, in very practical terms, to move from a distributed routing system in the internet into a centralized one. Now, this concept were there before OpenFlow, really. Okay? So they're not new in terms of concept, but OpenFlow really managed to put this into switches, into hardware switches, which kind of meant now, people that were not vendors, so, small companies or even universities could actually start and practice this new completely centralized system. Now, centralization today has become really key, and I mean, it's been there again even before OpenFlow, as I was saying, but with OpenFlow, really boosted that up quite a lot. It's key because it really allows flexibility in deciding routes and also opening up the system, which means that now you can facilitate the development of a new software, and I will discuss that a little bit more in detail. So just to say a very brief introduction, what is OpenFlow and what's the meaning of distributed versus centralized routing? Now, the distributed approach that we know the internet has been based on for many years, the idea is that each router in the system, it's an independent system, okay? They will run protocols, so they all run the same type of protocol so that they can converge in the way they find end-to-end routes. But the idea is that each one does it by itself. Now, router can be quite complex, but at the end, it all boils down into a very simple routing table where, basically, it's a table that tells what is the destination where you want to go and what is the port on the router that you need to use to do that. So that's the very basic of the router. So normally they will send link state information to each other to understand where each node is, what is the reachability of each node. They will each independently run a short path calculation. Normally the Dijkstra is an example of that. And the result of the routing protocol is to update the routing table. Okay, so it's all about filling in this table. That's what routing is really about. Now, the older distributed approach, each node is going to do that independently, and the algorithm is written in a way that after a time they will converge, which means that by following individual rules, the packet will go to the final destination. Okay. Now, problem can arise, of course, but we'll keep it simple this time. Now, OpenFlow is a centralized approach instead, which basically means the actual router, there are only hardware that they do have a routing table. So every router has a routing table, but they are not able to fill this this routing table by themselves. Okay, so they don't have the software to do that, and the software that does that is centralized. OpenFlow is the protocol that allows a server that runs the software to communicate with the hardware in order to fill in those switching tables. Now, again, things can get more complex, but this is the basic work. So, for example, if I use a reactive approach with OpenFlow, what happens is that if the router might not have any information on this routing table, so it does not know what to do when it gets a packet, sends it to the controller. The controller decides, because it has the view of the entire network, it decides what to do, and it will push this information down. okay, into the router, and now every other packet, the router does not have to connect to the controller because he knows already what to do because it's been written down in this table. Now, this reactive approach is not used a lot in the telecoms network. Mostly you do the proactive approach, where basically all the information, so let's say imagine that all the router starts with a blank routing table. The server is going to calculate all the routes, is going to find all those routes, and then is going to fill in the information on the switching table so that those routes can be effective, can be work effectively. So that's the way it works today. And if a new request, if a request for a new path comes in, same thing. The root, the server, the centralized server, which is now called the controller, the OpenFlow controller, is going to make that calculation, and then is going to update whatever router's routing table it needs to update so that the new path can be formed. So this is really, the concept of this OpenFlow and the centralized control plane. Now, over time, this obviously, I mean, if you can see OpenFlow, if you look at OpenFlow, it's really looks like a hardware level language. So, it's not something that allows abstraction by itself. And the abstraction was brought in by SDN. And, if you have to control a very large network, or even any network really, you can't just write things in OpenFlow. You need to start building level of abstraction, and that's what the SDN architectures allow you to do. So you can see that you're going to have a number of network devices. Then you have your control layer. This is your SDN control plane, and the SDN control plane has an interface. For example, OpenFlow is the one of the first one, the one we talked about, and with that interface, the control plane can basically command those devices, okay? Can insert rules and so on. Now, the controller is going to basically implement a number of network services that could be, calculate shorter paths, add quality of service, all these things. So these are kind of atomic functions that the controller could have. And then on top of that, you can write an application, and the application is really what allows you to create what you need to create for your work. And that is a bit like, you can imagine that the control plane has a built set of libraries, then the application I can use in order to make the network work whatever way it wants. Okay, now I'm going to be quick because this is kind of the beginning. Now let's go. So this is the software-defined network in OpenFlow. Now let's look at the network with virtualization in general, because this is another key element of this trend. Now virtualization is kind of like, you could think about it as something that gives the illusion of obtaining control of a physical entity or resource. Now, we know very well what virtualization is in computing because we can do that in our own PC and laptops. So the idea is that, the old ways you had a server, which is your bare metal was called. You put an operating system, and then you work all your applications on top. So there is a one-to-one match between the operating system and the server. The virtualization basically allows you to put still an operating system, but then you put an hypervisor on top of which you can put more operating system, and those can also be different. So VirtualBox you probably have used. You can see, you're going to have a Windows machine, for example. You can install on top of that VirtualBox, and then that allows you to install additional operating system, which can be all different from each other. Okay, so you can install a Mac operating system, you can install a Ubuntu operating system, and so on. Now, in data center, this principle is extended, of course, because you're not controlling just one machine, but you're controlling multiple machines. But in the data center, you can also see the real benefit that gives you, because now you can give people virtual machines without having to map them to always the same physical server. So you can reorganize your data center in whichever way you want. You can switch off half of your data center if you want to save energy, if it's not being used, and move all the virtual machine into the other half. So this becomes quite useful. Now, how do you apply this concept of virtualization into network? So the idea, here is that you use some kind of software to abstract the functionality of your network. Okay. So basically, in very practical terms, imagine you have a network which is made up of routers and links. So the routers with the interfaces, that's your physical network. Virtualizing it basically means that you can create a subset of that. Okay, imagine I have a software instance of that, and then which you can give to a customer, and now that customer can use that network without impacting anything else. Okay, so this is the concept. Now, the virtualization platform then is the tool that allows you to map these specific routers and links into the real ones. It's also the tools that allows you to create another virtual instance of that's built on the same network and make sure that those two virtual instances don't interfere with each other. Okay. And this can be quite complicated because you have data on one side. I mean, physically, the queues in the routers are the same, so you have to find ways so that the queues, the packet in one queue, do not interfere with the packet in the other queues. And this is something quite complex to carry out. Now, some example of network virtualization testbeds. These go from extremely local scale. For example, the OpenV switch is a packet switch operating in Linux environment. That's if you have an Ubuntu system, for example, that's inside your system. And if you have multiple virtual machines, for example, it allows you to send packets across virtual machines. Then you have Mininet. Mininet uses as well, again, the OpenV switch, for example. And this is a virtual environment that you can build in your laptop. But it allows you to build a number of virtual switches and virtual hosts. So you can basically build a network, an emulated network within your laptop. And then you can try an SDN controller on top of that network topology that you've done. And Mininet has become extremely popular. And it really allows you to test SDN controllers, okay, before you put them into the real world. And then you can go to global scale. For example, in Planning Lab, the idea is that you have virtualized nodes, and you can create a network through routers in a global scale. And today, these are these were the initial ones. Today, really, there's many others that exist, including in the wireless and the optical domain. Now, once you go into telecommunication, network slicing is like a step above, again, this network virtualization that I mentioned here. And it's basically slicing today is the concept that you can virtualize the network and create an end-to-end path across multiple network domains or technologies. For example, you might have a network that is made up of a wireless side, of an optical transport side, and some edge computing nodes. And the meaning of slicing is that you can have one network, and then you can virtualize this into different parts and have each part completely independent. But not only that, but each part is able to satisfy quality of service requirements. And if you go in 5G, those quality of service requirements can become quite strict. Okay. So network slicing is really the ability of having one, let's say, physical network, but being able to serve multiple services or even service providers and make them work properly. Okay, now this is virtualization. So I talked about SDN and OpenFlow, then which is kind of the control plane and the idea that you detach the physical hardware from its control. Then we went into the concept of virtualization, both from computing virtualization and network virtualization. But another, if you mix the concept of compute virtualization and the network virtualization, there's another things that come up, and that's of network function virtualization. Now, this basically means that you take a device, a network device, for example, a base station, and you virtualize it. What does it mean is that you take the software stack that a lot of time might be built into hardware and so on. You take it out, you build it fully in software, and then you start opening up all the interfaces. Now, an early example is the GNU radio, for example. And again, to put this into practical perspective, think of an old radio. Okay, maybe you were a kid, you open up an old radio, and you see a lot of, you see a circuit board with a lot of different things that you might not understand. If you look at the diagram for that radio, you realize that all of it is actually built in a way that is modular. Okay, even if it's in the same board, it's built into different functions. Okay, one part could be the RF, the radio frequency amplifier, which goes to the antenna. One part could be the modulation, and so on. Now, in virtualization, what you do is that you take that and you move it into software. Now, in order to do that, you need to digitize, but today a lot of this function can be done digitally. And again, you're going to have a hardware side, which, for example, is your RF amplifier with the analog to digital converter and so on. But all the rest, so modulation, encryption, error correction, they can be done in software. So think about this as a network function virtualization. Now, the advantage is that now you can adapt transmission format to environment applications, so you're not more rigid to the hardware, but with software, you can update things very quickly. You can coordinate with other radios and all these advantages that software and coordination brings. Now, you can think of also other network functions. Okay, for example, very typical is the one of the firewall in data center. Okay, now in the past, or sometimes even today, you used to have what's called the perimeter firewall. So basically, it's a big hardware that works at line rate for the entire data center that decides what can get into the data center and what it can't. The problem is that things are not supposed to get in the data center that they're a threat, but if they do manage to get in, they're gonna affect your entire data center. So that's the problem with the perimeter data center firewall. Now, if you look at VMware, for example, NS6 is an integrated firewall in each virtual machine. Okay, this is a much better solution that is allowed by network function virtualization, because now if something gets into a machine, okay, firewall one machine, it only affects that machine. It does not affect the other machines, because in order to affect the other, it will have to break into each individual firewall. It's also much better because if firewalls are really can be very application dependent, what you want to get through or not. So if you imagine that in a data center you want to do migration, ideally you want to migrate that firewall with that machine because it's linked to the application that you're running. And this is again an example. Now in practice, you can do everything that has to do with packet processing, for example, and switching are very good candidates for this network function virtualization. And these are examples: service gateway, broadband network gateway, and so on. Even the customer premises equipment, all of this can be virtualized. Okay, so this after this brief introduction, yeah.
Yeah, there's a question from Patrick. His question is, in this Mininet planning software, is it available for license to third parties for planning integrated wireless UHF, VHF, and Wi-Fi using Internet of Things mission critical communication solutions? So the main question is Mininet available for license to third parties?
Which one? Mininet?
Yeah. So this is a question by Patrick.
Yeah. So Mininet. I'm not extremely familiar with license types, but if you go into the Mininet website, you will see that it's been released under a license, and I don't know if it's like a new license. I don't remember what type of license it is, but you will see specifically what's allowed and what's not allowed to do. I can't recall because I never use it for commercial purposes. For research purposes, of course, you can do anything you want. For commercial purposes, I don't remember what are but these are very easily found in the Mininet website.
Okay.
Thanks. Okay, so now let's go into the interesting side. Is that how are we going to use this concept of SDN and NFV into telecommunication network? Now, first of all, software-defined radio. You might think, well, that's I heard that before, and used to be popular some time ago, but maybe you haven't heard about it quite recently. Today, cloud SDR is extremely strong and popular in telecommunication network. So if the concept of cloud run, the fact that you build a mobile network mostly based on software and using maybe data center, it's very popular. There's so many software, both commercial and open source. For example, SRS LTE, Amarisoft, FlexRun, OpenAir interface, loads of them that you can basically implement a base station on your own laptop. And we do in the lab, we do this all the time. Now, what is a cloud run? So a distributed run is basically, it's when you have a baseband all integrated in one box. Sorry, when you have a mobile cell, specifically the baseband unit, which is the processing side, all in one box. And again, a baseband unit or a mobile base station, it has a software stack, as anything else that does in communication. Bluetooth, Wi-Fi, they're all made of software stack. So your LTE baseband unit is also made of software stack, which is abstract. You can abstract by these components down here. A distributed run means that the actual box that's connected to the antenna the box is near the antenna, and it has all this software stack into it. The centralized run is the idea that you take this software stack. Usually, most of the time, you turn that into something that can run on a general purpose processor, so you can bring pieces of software, and then you run all that software in a server, and this could be in a data center, for example. I show you a Metro DC. Sometimes it has to be an edge node, and so on. Now, the very first way this was implemented was through CPRI, which basically means if you look at the software stack, only the radio frequency part was in the antenna side, and everything else then was sent through a fiber into a computing node. think of a small data center or something, and that data center would run all the other functionalities. And true, today, basically, there's a definition of an option for each of these split. And option means that you run one part. If you have the same option 7, you run ORF and LO-FI in the base station, and then you run everything else into DC. And there's a lot of options being defined. You can actually split this into 2, so you can have option 8 between an antenna mast and an edge cloud node, and then run the rest from the edge cloud node to the Metro DC. And even if you break down option 7, you can see that there is even more. Now, remind you of this option 7.2, because I'll let you know in a few minutes. This is becoming quite popular. But this is the concept of decentralized run. Okay, you really run things into software in a central data center. Okay, now the different, sorry, what I want to say here. Yeah, now the different piece of function, as I mentioned, can actually be implemented in a multitude of ways. You can see here that there is, so you can actually, first of all, you have to decide how many splits you can make. And normally you do either 1 or 2 splits. But here you can see what these are typically today understood. So there is a remote unit or remote radio unit that you put in the antenna mast, and this can have either just the radio frequency part, or else can have everything up to the high physical layer. Then you have a distributed unit which picks up from where the remote unit has left, so one of these 3, depending on what the remote unit does, and does all the processing up to here, option 2, or here in the middle, option 1. And then there is a centralized unit that does the rest. Okay, and you can see that you can actually have different options where you can have a remote unit that does one of these parts, but then it connects to this tier 1 side, or can have you can have the antenna side that does the remote unit and the distributed unit, or can also have up to the CU, centralized unit. So there are a lot of different options available. The main thing to remember is that why there are this differentiation between ORU, DU, and CU, and think about the interface. Okay, so between the DU and the ORU, you have a low-layer split interface. This is characterized by having very low latency requirements. This is very key for that, and somehow a high bandwidth requirement. Sometimes it's not extremely high, but it's anyway higher than the normal Ethernet data rate that you would have. Instead, between the CU and the DU, you have a high layer split, and this does not pose very strict latency requirements. They're kind of variable, but people say it's between 1 and 10 milliseconds. Normally, 3-4 milliseconds is okay. And the data rate is typically the same as the Ethernet interface. Okay. Now, ORAN is an interesting thing. So this is a forum, an industry forum, and this is standard. I mean, you have a lot of these options, okay? And these are even by the NGMN, which is a body. But if you want to make this sellable and deployable, you really have to define products. Okay. Now ORAN is really starting to define an architecture so that people can start building products on it. So he uses the split 7.2. This is being standardized that I mentioned before. And it means if you're creating hardware, you create hardware up to the 7.2 split. Okay, and everything else is being created by someone else. And this, basically the ORAN, what you really do, you don't really need to define what the software is. Okay, so the piece of software don't have to be open source, but you do define the interfaces, and that's the important part. So if you define all the interfaces between these functions, then every entity can build its own software there, and it can be open source or not. Okay, so this is what's happening from the mobile cell virtualization. Now, what's happening in the other side? So another important thing that's has happened in the last few years, is the concept of central office virtualization. If you take a central office, inside you find a lot of proprietary equipment. And for example, if it's a fiber to the home that uses PON, you find GPON OLT equipment. You will find Ethernet aggregation equipment. You find broadband network gateway equipment. And normally, if you're a vendor, you have to buy them. You can buy them from the same vendor. Sorry, if you're an operator, you buy them from the same vendor. Then maybe you can use just one management system, or else you buy them from different vendors, which means you have different management systems, and it becomes quite complex to do. Now, virtualization means exactly the same. You take this out. You realize that these are made of routing tables most of the time and some kind of software, and you decide, okay, can I open this up completely and do all the, into simple hardware which are basically very little more than switching tables, and all the software. And the software, I write it maybe in C++, C or C++, and I make it run on the normal servers. So the idea is that, remove all this proprietary equipment and build a small data center instead. Some of the, and this is going to be made of switches. And, if you look at these elements, at the end, they're all switches. And all the software that, does more the complex things, should be run in the data center servers. This used to be called cord. Specifically, the residential cord is the part that we're looking at the moment. And now the latest architecture is actually called SDN-enabled broadband access. So you will see SIBA now as if you go into the website and you try to download. And this is open source. Okay, so a lot of operators are trialing this at the moment. Now, there is more than cord. In fact, this can become quite complex. If you look at the ONAP, which is the Open Network Automation Platform, it's kind of an architecture which includes a lot of more functionalities that you see with respect to cord. This can quickly become very confusing. So I found an image actually from the Linux Foundation, which kind of put a little bit of order into that. Okay, at least you can see a software stack going from the disaggregated hardware all the way to operating system, network control, cloud virtual management, and this shows between all the different projects that you might have heard. It kind of shows you where do they sit, and that I found this very useful to understand what each of these does. For example, the telecom infra project is really about hardware disaggregation, data path and the abstraction. You find the OV switch, you find the DPD case, and so on. You can see that ONOS is here is in the network control, cord is network control plus cloud management, and so on. I found this quite useful. Okay, now let's look at the PON virtualization, which is really the work that we've been doing the last few years. Now, cord or SIBA today does the virtualization, for example, for the passive optical network. And the question is that big enough? Now, what does it mean to virtualize the passive optical network? It kind of means that, and this is what CORDS already does, that you can have a virtual network operator. You have one physical infrastructure, and then you can have one virtual network operator that serves a number of residential users, and then you can have another virtual network operator, which maybe serves base stations or small cells. And in principle, they can use the same hardware, but they are virtualized so that their functionalities do not interfere with each other. Now, is this enough? I think the answer is that it is. Okay, if you look at today's broadband, I think this is way more than enough. It's even better than what the people have used up to now. But notice that one thing that I want you to notice, and I'm going to come back in a second, is that the hardware, actually the whole MAC and physical layer physical layer is actually in hardware. Okay, that has not been virtualized. It's only the higher layer have been virtualized. Now, if you need to do multi-tenancy, for example, take this PON and current PON, and you have to do multi-tenancy. You have different virtual operator. Now, today you have high-level solution, which basically means all of this is in fixed hardware. Okay, and the virtual network operator will take. Let's say there are two virtual network operators, each serving different users, and they will take the packets from their user at a certain point in the network and then deal with them after that. Okay, but notice that today this part, which is the actual PON, the scheduling of the capacity in the PON, is actually still all in hardware. Okay,
Professor Marco, this
yes.
is Amit Alok. Sorry to interrupt. This may be a basic question, but what exactly is multi-tenancy in this context?
So multi-tenancy means that you have one physical infrastructure that you set up in the network, and this is common for access infrastructure because it's very expensive to put a lot of access infrastructure. So there is a fiber network, there is a network termination, and this belongs to an infrastructure provider. So it could be an operator, a big physical operator that owns that infrastructure. Now, virtual network multi-tenancy means that now you can have multiple virtual network operators that want to operate over that network and sell services. I mean, this is very popular in mobile networks. Now I don't know in industry what operator you have, but here in Ireland, the UK, for example, you have operators, old operators like Three and Vodafone that would have physical infrastructure, and then you have operators like Tesco Mobile. Tesco is a grocery shop reseller, but they can also sell mobile phone contracts. Okay, they don't have any base station, they do not own any infrastructure, but they lease they lease virtual network functionalities from physical layer. This is exactly the same. So there is an operator that does not buy infrastructure, at least not buy access infrastructure, and they have a contract with the infrastructure provider to lease some of their capacity. So that's the idea. Now that works pretty well for broadband networking. Okay, there is one problem, and that's why we went into what we call throughput multi-tenancy. Is that if you look at 5G today, that's quite different than normal broadband. Okay, especially if you look at the part that's mission critical. Machine communication, you have latency in the order of 1 milliseconds or less application to application, which you cannot satisfy if the scheduler, you cannot satisfy if you cannot control the scheduler. And in the current core infrastructure, you do not control the scheduler as a virtual operator. So that's where we came in and says, okay, now we have virtual operators which really need to put very strict requirements on the scheduler. How are they going to do that if there is only one scheduler at the physical layer? So what we looked at that, okay, why don't we take that scheduler, turn it into software, and virtualize it so that now the virtual operator, which has a virtual OLT, also has a virtual scheduler inside. And now you can map the virtual scheduler to the application that you're running. Okay, because the application has you got some kind of software. This is some kind of software. You link them together to an interface, and you can do that. Now, these are the publications that I'm mentioning that really you can look at there if you want to understand a little bit more.
But how does that bypass? Sorry, just a follow-up question on that. So, how does that bypass the latency requirement? Because now you are having two possibly different units working at their own time scales. And are you still able to manage the latency requirement of 1 millisecond, like you had said?
So, I will tell you. I'll make an example in a second to be very clear. Okay. So, this is a very specific example where this becomes extremely useful. But so the concept here is about that you schedule the packet depending exactly on what you need. Okay. So here, in the previous example here, you can do that. You cannot tell this guy here when to schedule. I mean, let's say a frame is 125 microseconds. There's no way you can tell you want to transmit in slot number 1, 15, 26. Okay, you cannot say that. You just have an average bandwidth over a certain number of frames normally. Okay, maybe every 4 or 5 frames. Here it's about you actually tells that you want to transmit in slot 1, 26, 27, because that's where your packets are going to arrive. I'm going to be more practical in a second. But anyway, okay, this is what you do. Now, the important thing is that if these are independent, then you will need some way of coordinating those two, okay? And we're doing a lot of work in that at the moment. But this is the real example, okay? Now, you might have heard about the fact that Cloud Run requires, especially if you do the low-level split, requires very low latency. And this can be in the order of 150, 200, let's say 100 or 200 microseconds just within the PON. Now, if you take a normal PON, you cannot do that, okay? Because normally, where the mobile station sends data to the ONU, then the ONU has to tell the OLT that it needs capacity. Now, this graph doesn't show that, but basically what happens is that the ONU has to tell the OLT it needs capacity. The OLT has to wait for all the ONUs to give that information. Then it calculates the bandwidth. It sends back down the information, and then you can transmit the capacity. So normally, this process itself, it takes a millisecond, maybe, well, half a millisecond or a millisecond, depending on a number of parameters, okay? So you cannot have 100 or 200 microseconds in any case. Now, NTT came out, and this is an example of the papers you can find, with an idea that, in this case, the smartphone transmits data because the baseband unit, the mobile baseband unit, has told it when to transmit, okay? Now, if you build a system with an interface so that your OLT can spoof that message, okay, can see when the smartphone is going to transmit, okay, because this is being already decided by the baseband unit. Okay, so the OLT only needs to read that message, so it starts doing the scheduling way before the actual packet arrives to the ONU. Okay.
Oh, so this is more predictive in some sense.
Yeah, it's called cooperative DBA. It used to be called cooperative DBA. Now it is called cooperative transport interface. Is being implemented, but that's the way. Now, if you notice, this kind of means now your baseband unit needs to talk to the OLT, okay? And if you have multiple base stations, with multiple, even used by multiple operators, you're basically going to end up with multiple schedulers here, okay? because and so having one scheduler doesn't work. And here is really where having multiple schedulers. I mean, this works very well with this. You have multiple schedulers that each follow a different base station, maybe, or a group of base stations. And now you can decide when. You can at least know. You can tell this guy when you need that information. Now, of course, you need some kind of. You will need coordination. And if you look at the last paper here, we'll start doing work in that direction. You will need some coordination. But now you have the ability to tell when you need the capacity. Okay.
Oh, you're saying the
Okay.
overhead of
Yeah.
coordination will still be within the latency requirement that you have. Even though you have like a hierarchy of schedulers, you'll still be able to manage the coordination within the latency.
Yes. I mean, one thing that I'll show you in a second, I'll show you the prototype. A lot of people thought, you cannot do this in software. We did it. Well, I'll tell you in 1 second what we did.
Thank you. Yeah.
So this is just to show how the system works. So you go from this model, which is physical, to this, which is virtual. So the idea is that the ONUs now they could send their DBRUs. So the information, these guys calculate their own bandwidth map, and they produce a virtual bandwidth map. And then this merging engine, it puts it together. Now, in the case of the Cloud Run, the ONUs don't send the message, but there will be the baseband unit that directly contacts the virtual DBA unit. Okay, this is an example. Now, this is already in a standard. You can look at the TR402. This system is already standardized, the broadband forum standard. I think there is soon going to also come up with another one called 370i2. I don't think it's been has gone out this already. But okay, this has been accepted also by standard. So we put it into the standard together with Vodafone, but it was also, Entity was one of the promoters of this idea. Now, some more interesting work is it really shows how you do one new thing, and this is going to trigger a lot of other interesting research questions. Okay. Now, one question that comes up is this. Now, we are in a system where now the virtual DBA creates their own bandwidth map. Okay. You see here. Now, think about it that these virtual operators will be competing with each other. They have different customers. They will be in different offerings. They will be competing. Now, if you think about it, any capacity, let's say this guy has 40% of the whole capacity, and these two have 20% each. Now, if these guys are not filling his 40% capacity every frame, there's going to be leftover room. Okay. Now, this means that the system will try to reuse that room because it makes sense in a PON to reuse that room. Okay, so you reuse the transmission opportunities. You don't waste capacity, right, in a network. You try to use it if it's free, if it's freely available. So the idea is that these guys have an average usage. Sorry, they have a guaranteed rate, which means they will always get that. But they can also have a peak rate, and this is really used across all telecommunication units, right? Operators use this all the time. You have a peak rate, which means this guy has guaranteed 20%, let's say, of 10 gigabit, which is 2 gigabit per second. But he can send traffic up to 4 gigabit, and if there is room, it will be accommodated. And this is used a lot across all the rules. Now this creates a problem because now this guy, anything that he doesn't use is going to go straight into his competitors. Okay, so his competitors can take advantage of what he doesn't use. So now the problem is this: because he can create a bandwidth map, he can create a virtual bandwidth map that pretends that he always uses his full capacity. Okay, he can do it because now it's up to him to tell what he needs. Okay, it's not the system autonomously deciding it. So this means that you're going to kill the ability of the PON to share capacity. So what we thought is that, okay, now you need to give an incentive to each of these guys to share his capacity that he doesn't use, okay, instead of pretending that he needs it all the time. And that's where, what do you do normally if you want to do that? Normally, you put up an auction, okay? That's what you do everywhere. Now, the problem is that you need to put an auction, but you have to run this every 125 microseconds, which is a bit difficult to do. And the solution is that you run something which is called, sorry, I think it's called single auction. Exactly. Sorry, one-time auction. So basically means that you don't have the ability to go back and forward with the price of the auction, but everyone sets his own price, and then the merging engine, when it calculates the capacity, it also takes care of this pricing system. Okay, and they can assign rewards to the different operators. So someone who has excess supply, for example, can sell the capacity with to other that has excess demand. Now, this is some work that we did with one of our PhD students, which recently graduated, Nima, and this is an very interesting paper to show that. So we improved the double auction mechanism from MegaFi, and here you can see the code. But the idea is that at the end, you can you basically can guarantee this desirable economic property of truthfulness, individual rationality, and budget balance. And that's what you will find in the paper. So it is possible. And the latency is not an issue because you don't go back and forward with your pricing. You just set the pricing once. You can upgrade the pricing if you want, the next frame, but you set it once for the 10, and then just the auctioneer calculates that. So that was an interesting work that we did, really nice. Now it creates another problem. Okay, third problem is that this works if these systems, market features, and these properties actually work, but there is one thing that you have to guarantee is that everyone needs to be able to trust the auctioneer. If everyone can trust the auctioneer, then in the system this is guaranteed. Question is that can you trust the auctioneer? Now, normally you would say yes, because you have an incumbent operator that owns the infrastructure, and then you have multiple virtual network operators, so there's no reason for them not to trust. Except that if you look at today networks, a lot of the time, this is the system, okay? You have a private incumbent, which is also allowed to serve services over that. Now, in some countries, this is changing. I think in the UK, I think they have separated this already. But, in a lot of countries, it is not. Now, you can see that, VNO2 is not going to trust VNO1 because it's actually the same. The auctioneer is also one of their competitors, okay? So you cannot do that. So what do you do then? Well, we thought about, okay, this could actually be a nice application for blockchain because you have a distributed, number of users. This is a private blockchain, sorry. A small number, but distributed users, more than 2. And they have trust issues with specifically the auctioneer. And the idea is that, okay, so can we use the smart contract technology? So we actually implemented it because it's important here to understand also what is the performance that you can achieve. And there's a couple of papers you can look at there. But basically what happens is that, okay, you can do this. Transaction rate is maximum 300 per second, okay? Now remember that an OLT requires 8,000 per second, okay? And also the average latency is around 1 second when you hit that value. So it kind of means, you're not going to do this real time. But even, this it can be used as a verification layer, okay? So you run your auctions. You don't run them you basically aggregate. You need to aggregate all the smart contracts because you cannot do 8,000 per second, but you could do up to 300 per second, although the rates of this keep increasing. So you aggregate that, and then after 1 or 2 or 3 seconds, you get the result. And that's totally fine because you probably are not going to do the verification of this every second. Even if you automate it, you might do it every minute and so on. But these allow you to build up again the trust system. Now, implementation.
Marco, one question here. So I just want to understand. So how often? So what's the time scale of doing this auction? And because you said they're dynamic, right? They're not static in that sense.
Yeah. So the auction is done every frame. Okay. Now, the way you put that information in the blockchain, you have to aggregate it. Okay. So you don't put the information on each frame in the blockchain, but you put aggregated information on each chain. Okay. So that's the idea. Or else, you could do the auction also aggregated, where you don't do the framing. You don't sell every individual frame, but you sell every maybe 10 or 20 frames. That's the number of options you can do that.
Okay, and one question here is, so you're basically using the blockchain to somehow not let one participant learn about the strategy of the other, in some sense, kind of keep the secret.
Well, it's not much about that. It's more about you want. No, it's actually different. So it's actually you want every participant to know how the auction was carried out. Okay.
But would it not help, for example, if we are competing and I kind of learn your strategy in the sense of what you're bidding for the auction? Could I not see or would you want to encourage it, or would you not want to encourage that?
Well, yeah. So it's an interesting thing, and I don't remember exactly whether that's how much of the information has to be shared or is required. I think some of it might be private. It's a trade-off, okay? So you might be able, because in blockchain you can decide who see what. The problem is that so you can hide some information, but you have to be careful then to decide if you hide that information, can you still double check whether there's been an incorrect way in the auction was carried out. So I think it's about this trade-off.
Okay. Yeah, because
And
you pointed out
it can be
one
tested
thing.
basically.
Okay.
Yeah.
Yeah, one thing you pointed out at the beginning was you did not want, for example, one entity to kind of hog a lot of the data, knowing that if it loses it, it may not be able to get it again. So it might kind of spoof some data. So in this mechanism, it seems like there may be a case where one entity ends up kind of winning the auction a lot of the times, and at least finding the social goodness in some sense might not work the best way. I don't know if
Yeah,
that is
but you see,
necessary.
yeah.
But yeah.
So I mean, but the thing is that basically it works like this. You're a VNO, okay? Imagine you
Mhm.
don't know what the other people are bidding, okay, in price. You
Okay.
put the price and you see you're not getting anything, okay? So the
Mhm.
next time, it might not be the next frame, it might be the next 10 over, after 10 or 20 frames or after a second even, you put a different price for the
Okay.
next ones, okay?
Mhm.
So, basically your strategy is going to change if you're not
Mhm.
winning any. Or if you're winning all the time, you then try to see, okay, can I try and win again with a lower price? So
Yeah.
this, the price can be continuously updated. You
Mhm.
don't do it every frame maybe, but you can do it, every few frames.
Yeah. Yeah. Okay.
Okay, so now is the interesting thing about, we talk about the virtual pawn, the theoretical studies, but it's very important that you also implement this. Okay. Now, this is work we've done together with Intel, and that's because if you want to run something at a line rate speed on a general purpose processor, you really need to know how to do that. So with Intel, we really understood how to use this DPDKs, okay, which is our key to run this type of packet processing at line rate speed. So we have set up, we have implemented this virtual pawn. So we have a pawn which is completely in software, and it's XGS pawn compliant. And then there are two options in the way this can be built. One is called high split, and one is called low split. The high split means that the part that you see here on the right-hand side is built as pretty much as C code, on a Xeon processor. And this other part, this 1, 2, 3, 4 elements, are actually instead in an FPGA. Okay. Now notice that so the virtual DBA, whatever case you consider, the virtual DBA is always runs in software. Okay, in both cases. The low split is basically means that absolutely everything runs as C code in software. Okay. Now this is not done because you want to separate, as in Cloud Run, one entity from the other physically. This is done to check, can you actually hit line rate speed by doing everything in software. So the result is this. If you use the high split, so if you do the function which are mathematically complex, like encryption, CRC verification, and so on, if you do them in hardware, like in FPGA, then you can get 10 gigabit per second with no problem. Okay, there's absolutely no problem running 10 gigabit per second. If you want to do everything in software, with the current Xeon processor, you still cannot reach 10 gigabit per second. These are some examples. Now notice that these at the moment run like Ethernet cards, so you can put multiple OLTs into one server and multiple ONUs as well. And this is really about understanding what is the performance that you can get from those systems. In our system, then we put outside, so the FPGA here for the high-level split are actually inside the system. These two are only the one that we added later on to do the burst mode reception, just to test in burst mode reception. But for this system, you don't actually need those FPGA boards. Now, these are when you run everything into software. So first of all, interesting, you got a 16-core unit. You can actually run 6 OLTs in one server. That's very interesting thing. And you can run, the virtual DBAs in other cores. And these some example that Intel reached. For example, these are, you can get upstream up to 5.7 gigabit per second, downstream up to 7.2 gigabit per second. Now, this depends on how many features you implement. So if you implement all the features in terms of error correction and so on, this will go even lower. But these are some interesting results showing that if you are willing to do this very mathematically compute intensive things in hardware, then you can get 10 gigabit no problem. And in one hand, there's no reason why you shouldn't do this in hardware, because these are very fixed things. Okay, you don't really change them from time to time. It's important to do in software all the things that have to do with like VLAN processing, scheduling. Those are more important to do in software. Anyway, so these are kind of a couple of papers that you can see this work going on. Now, another interesting thing of why you're going to do all this virtualization. Okay, one is for enabling that multi-tenants and multi-service that I mentioned, so that you can actually decide your scheduling. And we've seen the importance of. Sorry, I'm going to back now. the importance, for example, when you do the cooperative DBA, but also it's interesting to do the convergence, okay? Because the more you put in software, the more you are able to schedule across different domains. Example, we did a use case with the University of Bristol, which we have implemented it, okay? This is a hypothetical use case, but we implemented in our testbed to show how it will work. Now imagine that Bristol is a UK operator, okay? And there is a new network provider of augmented reality, we call it ARFlix, that is already using, is already distributing in the UK, but he wants to start distributing in Ireland, okay? Now, Bristol offered them the network services, but Bristol does not own any wireless infrastructure in Ireland. Instead, TCD, which is us, Trinity College Dublin, we own that infrastructure. So Bristol want to come to us and says, listen, I need some capacity, but I need capacity that I can control on your wireless system so that ARFlix can start selling services in Ireland. I say, okay, fine. But then the other thing is that, we don't really want to have that capacity 24 hours a day when it's not being used, okay? We want that when it is really needed, and we want to pay only when it's needed. So Trinity College says, okay, you know what, I'm going to do this. I'm going to give you a priority access to the capacity that you're going to pay for. But, it's expensive, but you're only going to pay for when you need it. Because the other time, my own base station are going to occupy that bandwidth. Okay, so this is the concept of the idea. The idea is that now we have an SDN control system, okay, that operates over the PON. So you do the quality of service over the PON and over the wireless system, depending on requirements from an application layer in another place, okay? And the orchestrator contacts our orchestrator, telling how to change the capacity over the PON and over the base station. Now I'm going to run this. I might need to, for a second, I might need to change my the video that what I'm sharing should be done in a second. Let me stop sharing for a second, and I'm going to start sharing a different one. Is it, okay, sorry. Just I should be able to do this in a second. Okay, here it is. Okay, so this is the actual example. So this is our lab that you can see all the again. Sorry, just you can see we are really running laptops for base stations. Okay, you need those USRPs, which are the radio front ends, but really everything runs in servers and so on. So I'm going to be very brief here, and so you're going to see a number of graphs. Okay, I'm just going to explain in a second. So basically, you will see that there is traffic. This is the traffic. The traffic properties. These are just keep alive message, but you will see that this is the traffic that will raise on the right-hand side. Hopefully, you can see my arrow. The traffic on the top right-hand side is how the traffic from Bristol increases. And then on the FFTs on the left and right, you will see on the left is the bandwidth. Actually, this is measured, with spectrum analyzer. The actual bandwidth used by the Bristol base station, the base station that's leased to Bristol. And the other one, FF2, is the bandwidth used by our own, let's say, best effort base stations. So I'm going to fast forward a little bit. So basically, you can see that as the traffic on the top right side starts increasing, we start, so the system interrupts for a short time, and then it turns up using a certain capacity. So at the moment, it uses 5 megahertz of bandwidth for the Bristol service and 10 megahertz for our best effort service, okay, because we use that. Now, as you see, after the bandwidth increases, 5 megahertz might not be enough anymore, so the system needs to increase the capacity, okay? Now, in this case, it's going to take a little bit of time, and I'll explain in a second why it's happening. It's taking so long. But you can see that after a small amount of time, now the system turns up again with 10 megahertz. Okay, so we give now more wireless bandwidth to Bristol than to our own base station, and this keeps going up and down depending on the requirements. And I don't want to stay here too long time, so I'm going to go back into sharing my own presentation. Okay. Now the reason why it took so long is actually when we did this only on the physical layer, we could do that in less than half a second. The problem is that in order to be implemented in the Mac, this is not part of the way the system, the software stack was implemented. So you need to reboot the base station. But you can just recode the base station so that you can do a fresh start. So, but in that case, it takes some time. So this is an interesting work, again, that we did, showing what you can do when you start virtualizing multiple systems. Now, an interesting work we've done on the PON, and this is my last slide on the PON, is the edge problem. Okay, you've seen before that we have, you're not going to have macro stations connected to a number base station, edge nodes, and so on. Now, there's a lot of work today where you use a passive optical network to serve small cells. And the reason is that it's very cost effective. So it is very expensive to give one dedicated fiber connection to each small cell. And people are trying to use PON. Now, PONs are very good, very low cost, but they are in a point-to-multipoint architecture, in a tree architecture. Now, if you notice, this new edge system is not point-to-multipoint. It starts looking more and more like a mesh architecture. The problem is that how can you use a PON, which is a tree point-to-multipoint, to satisfy a mesh type of architecture? Okay. So here, for example, in a PON, this guy, the small cell, has to talk to the central office, and then in order to talk to the macro cell. But if the small cell needs to talk to the macro cell directly, then in a PON you cannot do that. Okay. So here where we come up and we're doing some work on trying to mesh the PON architecture. So trying to have a small cell being able to communicate directly with ultra low latency to the macro cell, edge-to-edge communication. Okay. Now this becomes quite interesting because there is a real requirement for this type of communication. Now in this case, we use, in the splitter, we put a reflective filter so that a certain channel can go back towards the axis straight away. You can do it in different other ways, and I'm going to go a little bit quick in here. But the idea is that, if you put this, then you start conceptualizing the concept of creating virtual groups across the entire PON. Okay, so we have a number of small cell here, here, and here. They might communicate with one OLT with an edge node, or else they start communicating with a second edge node, depending on traffic and so on. And very quickly, these are some examples, and Sandeep Das, it's actually a PhD student, has done that work. And you can show, for example, how you can use this to multiplex connection over multiple OLTs. For example, you have a number, as the traffic from an OLT, from the ONU to the OLT starts increasing, you will start seeing delay. But if your delay max is 100 microseconds, at a certain point, you're going to break that delay. Okay. So here, you can simply add another OLT from the edge, on the edge side, and offload some of the venues to that OLT now. Okay. And you can see that you can keep taking things on the edge again, but you can reduce the latency, and you can do that in different ways. I'm gonna go a little bit quick here because I'm running out of time. And these are the publications.
Sorry to interrupt you. In the previous figure, you have shown that the 40-kilometer distance from the central unit to that remote unit. So, are you able to get that latency means within that distance?
Yes, because now you see you don't go from these guys. You don't go all the way up here. Can you see my mouse pointer when I use it?
Yes.
Okay, so you don't go here. The concept of this is that you have an edge node here, real close to it. So you only go to the level 1 splitter, which is a few hundred meters away, and then your signal goes back. So now your distance is not 40 kilometers. Now your distance could be like 500 meters or 1 kilometer. And this is completely optical. There is no delay here.
For that edge network, which split you have followed? Lowest means where you have taken the split?
So this thing is a power split that you normally goes up. But if you put a reflective filter, let's say wavelength 1, now can be reflected back. So the message from this small cell is reflected back to this edge cloud node. And there's no protocol here. This is just a straight wavelength reflection. So you only have a propagation distance of a few hundred meters to do this connectivity.
Okay.
So this is the idea. So you don't have to go back to the central OLT in the central office, do the packet processing, and then transmit it back. The idea is that now you can enable direct communication within edge nodes, which is something that in a normal PON you cannot do. But this is now becoming, I know that a number of vendors are becoming very interested in this approach.
Okay, sir.
And it just shows some example of how you can use it to offload traffic to a different OLT, because now the idea is that you can have OLTs here at the edge. So this is about it. If you have an OLT at the edge, then you can put an edge node. And you can put multiple OLTs, you can put multiple edge nodes. So you can do also load balancing. Now, I probably have another 10 minutes. Apology for this. I'm going to do a bit quick here. Now, this just to say that we're talking about...
Yeah. Sir, I have a question.
Yeah.
Sir, when you are putting a sort of like a virtual dynamic bandwidth allocator at the level one, L1 splitter, then then the passiveness of the PON is gone, na? So it is like the active optical network, na?
Well, no, think about this, okay? I can create, so this here, the power splitter is all, so this splitter is passive. Okay, it's passive from a protocol
Yeah.
perspective. Now, depending on
Okay.
loss, you might need an optical amplifier, okay? But that's no problem. I mean, today even standards are allowing optical amplifier on the central office, the standards, okay?
Okay.
So not yet at the splitter, but again, this is, it means it might need electricity, but does not do any packet processing, few watts of electricity.
Okay.
And
Okay.
this is probably in a cabinet, so cabinets normally tend to have electricity anyway. But the idea is that from a protocol perspective, this is transparent. So your wavelength, your optical signal goes here and is reflected back. Okay. So the OLT runs DBA between these two guys. So it does, from a protocol perspective, there's no difference if your OLT sits here at the edge or in the central office. It's exactly the same. It's just that physically this reflection of the wavelength allows you to put it in there. But protocol-wise, is exactly the same. Okay, there's absolutely no difference.
Okay, sir. Okay, sir. Thank
Now,
you.
the other thing I would just want to touch briefly is this. We have disaggregated the Cloud RAN, we have disaggregated the telecommunication central office, we have disaggregated the PON. Now, what's happening on the optical layer? Because, if you want to keep together, if you want to look at this picture, there's a lot of optics. So you may want to ask, what's happening at the really very physical layer of the optics? What's happening in there? Okay. Now, today, today things are being disaggregated, but the legacy view of an optical network is that you have a number of elements. You have transponder, multiplexer, amplifiers, ROADM, which are kind of optical switches, optical wavelength switches, and their control plane, typically a line system control plane to control the real transmission path, and then the higher level control plane to control all the system together. These are all from one vendor. Okay. So you have to go to a vendor. I'm not going to name any vendor, but go to one of the vendor and you have to set up your system with them. And that's the only way these interoperate with each other. Disaggregating means going to this side. Okay, so you basically build an optical network by mixing and matching equipment from every vendor. Now this is an extreme view. For example, today what people start disaggregating is just transponders from the rest of the system. So you buy the line system from one vendor, but you can buy a transponder from a different vendor. And this is the first step. But the full extreme view of disaggregation is just you just buy these as if they were Ethernet switches, okay, and use an open flow type of system to put them together. Okay. Now, what you're going to do then, you take ONOS, for example. ODTN is actually from the ONF, is the part that look at disaggregation of the optical system. But you took ONOS as an SDN controller, and you you change ONOS, you upgrade ONOS so that you can also reconfigure these ROADMs and amplifiers and so on. So this is the concept. And the research is going to this side. Now, why is taking so long compared to the rest? The problem is that here you're not disaggregating a digital system. Okay, so a switch, switches, router, these are digital systems. So you need the proper APIs and so on. But if you put a bit to be 1, the bit is going to be 1. Full stop. It's digital. The physical transmission, the optical transmission system is an analog system. You're transmitting waves. So you're dealing with the continuous physical quantities, which basically means there are things that is very hard to predict how they're going to work. There's no linearities, there's noise in the system, and you're not really sure how they're going to work out. So you cannot be deterministic and say, I'm going to set up a path and it will work. It's not like a VLAN. You set up the bits in there and that's automatic. Here you set up an optical path and you might see, okay, there's too much noise, it's not going to work. So the problem is the problem of margins, okay? So when you build an optical system, you build margins, which means that, this is measuring dBs. It could be OSNR, optical signal-to-noise ratio, or it could be power budget. But the idea is that, you expect that the system will work if you put a margin of 3 dB. Let's say you make the system with 3 dB more margin that you expect. And the idea is that, if something goes wrong or something you didn't predict correctly, there is still 3 dB to be used before the system breaks down, okay? Now, what's the problem with margin? So this is a paper again we produced with people from Arizona. The problem is that if you want to be 100% sure that your system will work, then you put very conservative margins. You put maybe 5 dB of margin. The problem is that putting margins means that you are not going to attempt to create some paths because you think the path might not work. That's the idea of margin. If I'm very conservative, it means some of the path I don't think they're going to work. Okay, because I think the noise is too high. So when I add 5 dB of margin, my system goes above threshold. And that basically means your network utilization goes down. If you are less conservative, so more aggressive margin means, I only put 1 dB or half of dB of margin, then you can create a lot of paths because now you think you only have to add half dB to your calculations. And, most of the time that will be fine in calculations. However, because you're being aggressive, there are a number of paths that are not going to work because, their margins were there exactly for unpredictable things. So when things that you cannot predict well happens, your system is going to fail. And this is an even bigger problem of being conservative. Now, people have done examination on this, and they say, how much does it cost to add margins, to add more margins in the system? And again, sorry, one thing, if your system, these systems are highly engineered, okay? So these are engineered by people who know exactly how each individual element behave. If you open this up, you lose that information. Okay, you don't know exactly anymore how things behave. And that's why you need to put more margins. Okay, so that's why I'm talking about margins here. Now, people have done, operators have done some analysis and says, if you are in the core, margins are very important in the core because that's where most of the core is. And they realize that, it's very hard to open up the system, disaggregate the system in the core. But if you are in the access and metro, this graph at the bottom shows that you can really waste your margins. Because the system itself does not need such type margins. This is just I thought it would be interesting to add this into the discussion. Okay, so the problem is that, okay, so what do you do this? Because even if you look at this picture here, you don't even know where you are in this figure. What is this point where is the best margins to use? You don't know that. And every system is different, okay? That's why you don't know that. Is this 3 dB? Is this 1 dB? Is this 5 dB? You don't know. And if you don't know, you don't know where you put yourself in the system. That's the real problem. Now, this is also, one of the examples that why do you not know this? Because, the fiber length, the nonlinearity, there's a lot of physical models that you can use. The problem is that there are devices in the system which are not easy to, they're not easy to characterize. For example, amplifiers, they have a non-flat gain curve. Now, the vendors do try to put filters to flatten it, but the filter is not perfect. It depends from device to device. So you cannot flatten for different devices. It depends on the operation point. So at the end, there is a residual gain that is not flat. Now, this means that as you start putting channels, some of the channels are going to have higher signal-to-noise ratio. Some of the channels are going to have lower signal-to-noise ratio. These amplifiers are on a chain, normally, one after the other, every 50 or 80 kilometers. So the idea is that you actually don't know how the network operates, and people have used machine learning quite a lot to try and estimate that. This is some work we did, for example, based on simulated data. Now, there is a lot of work that people have done on this, so you can, if you look at our publication, you will see some references, also using real data. But really, there's a lot of work being done on machine learning on trying to understand what is the signal-to-noise ratio across different wavelengths, for example, so that you can, reach a much better have a much better prediction of whether your system works or not. And prediction is important so that you don't have to be conservative on your margins. Okay, this is the idea. While still, prediction is important to really understand how you get into this part of the curve. Now, interesting. So what this tells you is that now there is a lot. Once you open up the system with the interface, you're going to have a lot of software. There's control plane software, but there is a lot of intelligence software. Okay, that you start building up. Now, the idea is this. Now, has Mininet was built for so that you can test an SDN control plane, on a network of switches and routers. Now, wouldn't it be great if you had a system that you could test your optical layer control plane, so this control plane here on the system, so you can actually test, does it work? Is this algorithm, does this algorithm, machine learning algorithm that I'm using, is that work? Can I collect OS signal-to-noise ratio information in the network so that I can inform better my machine learning system? And I can do that in an algorithm, but where do I test my algorithm? Okay. And that's why we created a new mininet, which is a mininet optical. This is a collaboration within us, connected Trinity College and the University of Arizona, Professor Dan Kilper. This is still ongoing, but basically it's an SDN emulator that uses mininet and additional physical layer optical simulation so that you can emulate optical devices such as ROADM amplifier transceiver, fiber propagation with nonlinearity, and each of these is basically a mininet element. Okay, so each of these is basically a switch, a mininet switch, but we augment that with different functionalities, for example, wavelength functionalities and so on, and with a physical layer emulation tool. So now you can put a NONOS optical controller on top of this. So basically now you can create a topology, you can put ROADMs, you can put amplifiers, fiber, whatever way you want, and you can now put a controller on top, make your controller work, and see whether it works or not. So you can find if your system is consistent, if your interfaces are consistent, but you can also, as far as you trust the optical simulation, again, a simulation is still a simulation, you can check whether your machine learning algorithm works. And we even have, we even reproduce this type of figures in the optical amplifiers. Okay. And these are sample figures taken from real amplifiers. So you can really see whether your machine learning, given the data you have, is actually performing or not. But it's not just the algorithm. You can actually check the entire controller. Is the way I collect monitoring data okay? And the idea is that, then you can move this into, much quicker into a production system. Now notice that this is we can always say this is the real thing, because if you notice this publication that the first time we published this system, Bob Lance is the person in Stanford who produced Mininet. Okay, so we're actually creating this Mininet optical with the person who produced Mininet on the first place. So we have a full view on how the system operates, and so we're still now working on optimizing the system. Few publications will come up soon, building also the documentation, which at some stage in the future this will be released for other people also to use. Now, just want to go to the conclusion then. So I think the conclusion that I want to make is that this disaggregation of system is happening, okay? And it's happening everywhere. It's happening on the cloud RAN, it's happening on the central office, on the virtual PON, it's happening on the optical layer, and so on. And this is not just being discussed by academics. This has passed into industry, not only into discussion forum like the next generation MN, and the NGMN. It's now going into forum like the ORAN from operator that's really looking, operator and vendors, how do you put this into production, okay? So when there are already people building completely disaggregated small cells you can buy, there are people building complete and selling disaggregated OLTs, like EdgeCore is selling white box OLT switches. And people are selling white box ROADM, like Lumentum is selling white box ROADM. So this is really going into production. The other thing is that, so we are having a huge amount of flexibility built into the physical layer technology, okay? Be it Cloud RAN and so on. So the fact that you have access now to the software, to the interfaces, you can actually build intelligent software, okay? And you can do this because the flexibility that the architecture allows and the physical layer allows. Even at the optical layer, you have FlexiGrid ROADMs, you have things which are not yet product, but the micro ring resonator technology, which can do wavelength switching extremely quick. In transmission, you have coherent transmission that's moving towards the axis, and coherent transmission provides a lot of flexibility. You provide complete flexibility on dispersion compensation. It provides a higher budget, which means you have more choices of where your connection can go. It provides much more tunability in the wavelength. So there is a lot of flexibility built into the network. The real thing is that, okay, what's next, okay? And I took the idea of using this picture again from Dan Kilper, University of Arizona, because, back in the times when the people were trying to fly, it's not that people didn't know how to fly, okay? People knew how to build engines to power the plane. People knew what the wing should be in terms of getting the ability of producing the difference of pressure that allows the plane to fly. The problem is that people could not make the plane fly for more than a few hundred meters before crashing, okay? So the problem was not the hardware. The problem was the control, Okay, the Wright brothers, what they got right wasn't the wing profile, wasn't the engine, was the understanding that they need to provide flexibility, a way to control wings flexibility. Okay, once they did that, they managed to make the plane fly. Okay, and so it was all about the control. Okay, it was not about the lack of other powerful mechanisms. So I want to say that, because we have so much flexibility, so much interesting hardware coming up, really it's about the control is the key here. How can I make full use of this flexibility? Okay, and the problem is that how do I solve the complexity? Okay, and there's complexity itself in the physical optical layer, but there is even more complexity once you try to put the physical optical with the cloud RAN with the virtual PON. So how do you manage this flexibility automatically? Now, there's a lot, and that's why you can say that there is a lot of work. I mean, people are already working on this control, right? And there's a lot of work that's gone on machine learning techniques because the systems are so complex that you really want a way that the system can learn really from its own use. Okay, so a lot of work in that. Now, what is next here on the machine learning that's coming up now? See, the problem with machine learning is that machine learning learns how to work a system by itself, but that's not exactly what you want. You want machine learning to figure out how to work the system so it can do things that you want. Okay, so you don't want machine learning to do his own things, You want to make not his own decision on what he wants or he has learned. You want machine learning to learn things so that then you can tell him exactly what to do. This is the real key. So machine learning now is moving towards including human in the loop, and that's something which is also called explainable AI. And it's about you want the system to learn all the parameters, but then you want to be the one that really tells what it's supposed to do or not. Okay. And I think this is the really interesting things that come up. Now, just before I finish, I mentioned that so we are basically building in Dublin now. This Dublin is called DublinNets, and it's an end-to-end testbed, and it's going to be based. We are building it at the moment. It's going to be based on an open interface and open source software. And it's really about this is one of the key problems today. So as you open up all this system, how do you make it work together? How do you integrate it? And it's all about building this control, okay? So we're going to have this infrastructure, which is partly based in the lab, partly based around the city. And, you can see on the left-hand side, going to have outdoor 5G small cell, edge central computing feature, fully configurable optical network, dark fiber connectivity across the city, and in the lab, so, over 1,500 kilometers of fiber, and the virtual PON technology. So how do you put it all together so that this can work out? This is meant to be out before the next year. Before the end of next year, probably mid of next year. And so last thing, this concludes my presentation, and I hope it was useful. And again, I'm available to take more questions here online. Just want to say that, again, we are hiring actually PhD students at the moment, especially now that we're going to put this system in place. Really, we want to work on this control key issues, and we work on that on a real environment. Okay, so we have there's a lot of open source software for Cloud RAN. Now we have things for virtual PON ourselves. We have this mininet optical tool. We really want to crack this system open in a real environment. We want to put emulation and real environment together, and we are hiring now PhD students to do this work with us. So that's it. I hope you guys enjoyed it. I'm sorry that I went a little bit further, but I took a few questions during, so I think that's delayed a little bit the talk. But again, thanks again for the invitation. If you have any questions, I'm here for you.
Thanks a lot, Professor Marco. Yeah, if there's any question, please go ahead and ask. Be nice.
So I don't know if I have a chat, but you probably have a chat. There is a chat.
Yes. Yeah, there were a couple of questions in the beginning, and that was.
Yeah.
Yeah, there is a question from Samaresh. He's asking you whether you're considering a cross-layer design.
Cross-layer?
Yeah.
Yeah.
The question is,
so is it
cross-layer design? Yeah.
Yes, I mean, if you think about this, so yeah, I don't have this probably on a slide that could have been interesting. I'd remove it for this presentation. Otherwise, be too long. But yeah, so cross-layer, I mean, here there's two things, okay? There is horizontal. You think about the stack as organized horizontally and vertically. Horizontally means that you move across different technologies, okay? So you basically move from a base station, and you have a protocol stack of a base station, to an optical system. You have a protocol stack of an optical system, and you have an edge computing system. You have a protocol stack to manage the edge computing system, the edge central and edge computing. So on one side, there is challenges about the horizontal integration, and the example we presented with Bristol, for example, or the coordinated DBA is one example of solving that. So sometimes you have to solve cross-layer issues, but horizontally. So how do you make the wireless scheduling talk to the optical scheduling so you can minimize the latency? Okay, so that's an example, and that's shown in there. And then you have the vertical one, which is more about how do you make the application layer synchronize with the physical layer, or else how do you figure out the layer 2, layer 3 routing with the optical layer routing, okay? And these are all things that, these are all things that we are considering. I mean, in fact, this optical mininet
Sir, I have
really,
a question. Sir,
sorry, the optical mininet allows you to put together both the packet switching of mininet with the optical control and the switching of the mininet optical. So that's something that is very important.
sir, I have a question, sir. Sir, regarding when you are doing a blockchain-based trade-off, okay, or blockchain-based auctioning of bandwidth, then are you storing the information about the transfer of each and every packet? Because then the information that the blockchain have to store will increase extremely fast. So
No.
what will?
So notice here, okay? So the only information that you need to give is that how much. So basically, sorry. The information that basically has to go to the chain is that how much capacity each virtual network operator making available. Okay.
Okay.
So there's not about, you don't need information about packets.
Yeah, but you don't need information about the packets. But this information in the blockchain, it is normally what is done is that the information is always stored and it is never deleted. So the chain will grow longer and longer and longer very fast. And there are millions, trillions of packets going. So
yeah, but so imagine this, okay, yeah. So I mean, if you look even, I mean, these are trade-off, of course you can consider. But even let's say you look at 100 transactions per second, okay. So this information is really, you basically each transaction is a few bits of information.
Okay.
Because let's say you have 5 operators, you have 100 frames, and then you have each operator gives a value of bandwidth and a value of price. And that's it. Now the other thing to notice is that, so what you said about blockchain is true, because you're now thinking about bitcoins, and in bitcoins you kind of really have to keep track of all the the virtual money strings, so that because you don't know who has it, who is going to use it, and so on. But this is a private chain. Okay, first of all, there's a very small number of users. Because the users are virtual network operators, and the other thing is that you can actually things that are 1 year old, for just an example now, you don't need that anymore, because you can say, you can decide and say
you will be deleting extremely old information actually.
Yeah, as an example, right?
More.
Yeah. So you could tell all virtual operators that the data is going to be valid for 1 month or for 1 year. So you have to make any problem you have to tell it within 1 year. Okay. So that's an example how to solve it. Yeah.
Okay. Thank you, sir.
Hi, Marco. This is Sachin from NCI.
Hi, Sachin.
Thank you for a very good presentation. So I saw that you also talked about explainable AI.
Yeah, very new.
Yes, it's very new, and I know it is very challenging because AI is a black box approach. So I just wanted to know, what are you doing there? Because I also try to do it, but because we have very limited models, explainable AI models, so it is actually very hard to do it in telecommunication world. So
yeah, this is extremely new. So we're just putting a proposal together.
Okay.
So absolutely, yeah, this is extremely new. So I don't have a very strong view on this, how can it be implemented. It's just something that really starting proposing now to see how it can work really.
Okay. 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 Thank you for it.
And in the next year or two, maybe we will know more about that.
Okay, yeah, because it's a new field, so
exactly.
it was challenging to me as well because I was doing it, but it's hard to do it because there are very limited models. So
yeah.
Okay, good, thank you.
Yeah, and I mean explainable. On one hand, it can be because you want to be sure that your system is not going to misbehave on something you're not predicted.
Yeah,
that's one way.
Okay.
But the other way is also here that I think it's also about you want machine learning to be oriented. You basically want to be in the loop, not just to check, but also to make sure that you can tell the system. So the system can learn in a way that is useful for you, rather than just automating everything. I think that's one of the keys. But explainable AI I think is very interesting. But really, here the control is the key. Okay, so I think explainable AI is one direction that the machine learning could go to help with this issue. But really, everything that has to do with control plane, so anything that has to do with interfaces, anything that has to do with intelligence and automation, this is all part. Even the older machine learning, there's still a lot of things that can be done with that.
Yeah. Okay. Good. Thank you.
Okay. Okay.
Hello, there is one question in the
Yes.
chat box. It asked by Professor Wasim Arif. He's asking remark on energy constraint. Considering low energy edge computing enabled system connected to RRU.
Sorry, can you repeat the question? So this is about the
remark on energy constraint. Considering low energy edge computing enabled system connected to RRU.
And what is? I mean, the question is about energy constraints itself, or? But, I mean, okay. Let me take this. Okay. Now, I mean, so I mean, I'm not sure exactly where the question goes, but let me say that. So this remote unit is a small cell. Okay, so a small cell needs to be powered. Okay, and needs to be powered because it has a radio amplifier, so it has a high power amplifier. It's a type of service that's not exactly like IoT. It's a service that's on all the time. And the other thing is that a small cell is very typical of urban environment. So let's say if I need to cover a very large area, okay, I'm not going to put a small cell. I'm going to have to put a macro cell and so on. So small cells are typically urban area where power is widely available. Okay, that's one thing. The second thing is that that's why normally you will find edge nodes in what are called cabinets, and cabinets typically have power. They could be embedded with a lamppost, which does have power. So I think, the energy consumption, I think it's a general question about energy consumption of edge nodes, I think, whether they do remote radio units purpose computation or they do other type of computation. And, there might be issue about does this increase every energy consumption in general or not. That could be something to discuss. But in terms of, energy usage, normally these are in position where there is energy available. In fact, if anything, the real problem that we see today in when you want to install small cells around the city is not that energy is not available. Is that how do you calculate the consumption of energy? Because energy needs a kind of a counter in order to count the energy and in order for you to pay for the bill. So these are actually problems that comes up. Not the fact that there is no energy, but the fact that how do you count the consumption so that you can pay a bill somewhere in the middle of the road without installing a meter in absolutely every place. So yeah.
Sir, I have a question, sir. In optical in ponds now, that is, these amplifiers are mainly placed only at the OLTs or at the cloud. Nah? It is never placed in front of the splitter or around the splitter, not like that.
Yeah.
It is always placed at the OLT or at the cloud. Isn't it? Like
I'll tell you a second. Let me take the. Yeah. Okay. So today, if you look at the standards today, and most, like 99% of the way it's implemented, there is no amplifier in a PON. Okay. So a PON is a system that covers 10 to 20 kilometers. The splitter configuration is in a way, and it's all configured in a way that you don't need an amplifier. And that's fine. It's always been used for type of broadband system with current central office locations, so it's always been fine. Now, the concept of amplifier has been raised in the past when you change the architecture. For example, we did a lot of work on what's called the long-reach passive optical networks. It was a concept that BT put together back 30 years ago. And there, the idea is that you put your central office not 40 kilometers away, but 100 kilometers away. So you need a much smaller number of them. And then, you put an amplifier at one of the splitters so that you can, with a small amplifier, you can basically reduce the number of central offices by a factor of 100. So this is the type of calculation. Now I know that Google has, this was a project that we did, and I never went to the standard, although it was discussed in the standards. But now I know that Google has put it back again with the super PON concept. Now I think in the super PON, I'm not sure where they put the amplifier. I think at that moment they try to put the amplifier just at the central office. Okay, and physically is not. I think it will depend. Okay, if there is requirements for putting an amplifier in the ODN, it might be put in there. Okay, especially I think this becomes helpful if you start putting not just a passive splitter, but some other technology. For example, here we use tunable filters. Tunable filters don't need a lot of power, but they need some power for when you change, from a configuration to another one. And the moment that you need a few devices that need a little bit of power, then I think putting an amplifier there is much less of a problem because you put in power. But yeah, I mean, this again is an architectural, it's a research type of architecture. In our case, we need an amplifier sometimes, not all the time, because we have to go. The signal goes twice through the splitter because the filter is behind the splitter. But you can think of technology today that might allow you to do something similar without having to go 2 times across the splitter. Okay, so there are some kind of configuration that are less flexible but allows you to do that. And in that case, maybe you might not need an amplifier. Yeah, but things change depending on requirements. And I mean, the amplifier requirement, does not require a lot of complexity to put an amplifier in there. It does require some power, but so I think it really depends. If it becomes really required, I think it's not going to be a big issue putting the amplifier there.
Any question? Okay, I have one doubt. Hello, any question?
Yes.
I have one doubt regarding the functional split. As you have some
Yeah.
papers you have shown some functional split. My question is, which split you have followed? Either you go for a fixed functional split or dynamic functional split. Fixed means once you split, it's fixed. You cannot change. Dynamic split means as per the application, you can change the split. Second question is, in follow to that second question is, if you have followed any split, where you have made the split? In which layer exactly? And why? What's the reason?
So you're talking about this slide, is it correct?
Yes.
Okay. So let me add the first question first. Now there is, there are papers. Okay, I've seen papers looking at dynamic split. Okay, I don't think it's an issue. I think it's about really having a strong use case, really important strong use case that requires that. Okay. I mean, the problem is this. Let's say you have a flexible split that allows you to change from split 6 to split 8. That means that your remote radio unit has to be able to handle the worst case scenario, which is up to split 6. Okay. Now, if you have that, why would you go back to split 8 once you have put all the hardware in place? Okay. Now, I have seen there are some use cases that can be considered. Okay. So, for example, is that if you use split, because split 6 is better in terms of optical layer requirements. Okay, so your latency is strict, but is not as strict as CPRI, and your bandwidth is actually quite low. Okay, compared to CPRI, so it's a good split to use for optical transport perspective. So in principle, if you can use split 6, you'll always use split 6. Now the only counter argument that I've heard is about sometimes if you want to use higher power in terms of MIMO, if you go to split 8 allows you a much better control of the MIMO system. Okay. Because basically, if you want to coordinate the transmission across multiple base stations, then you want to run the MIMO layer in a piece of software across multiple base stations. Okay,
Actually,
so that you can send.
Yes, I'm little bit worried about the energy consumption as I am working on UAV. So I am worried about energy consumption because as you go for more split options, then definitely the energy consumption at the remote head will be increasing. So
Okay.
definitely.
Yeah, but in that case, like, are you talking about the UAV as in the base station is in the UAV?
Base station UAV as the RRH, remote radio.
Yeah. I mean, so okay, if you consider that case, I mean, I don't really work in that way. Just if I had to think now, just now. Okay, I mean, in there, why would you be flexible? Because if you are flexible, it means you're going to put computing elements in the UAV, which are heavy, which means you have to increase your the energy of your engine and the power consumption of the engine. Now, when you talk about UAV, think of energy consumption as a whole system. Okay, don't separate the energy consumption from the engine that keeps it flying from the energy consumption of the base station part. Okay, because it's a isolated system and you have one battery. Okay, so if you do something that decreases by factor of 2 the consumption of the base station, but then implies for some reason that your consumption of your engine goes up by 3 times, then there's absolutely that doesn't work. Okay, so always think about the trade-off of the energy consumption of the radio unit versus the engine. Okay, so like if you think about it, okay, maybe if you work here. So I mean, my point is this: like if you put more computation into the UAV, you're going to consume more energy. Okay, so in that case, why would you have anything flexible? So you're better off putting stuff in here. Okay, you only put the RF with no computation. Now then the problem comes: can you have a reliable connection that satisfies this data rate? Okay, maybe not. So maybe you say, okay, you cannot satisfy the data rate. Maybe I want to have a split in there, but I fix it. Okay, and the idea is that if you try to be dynamic, you have to be careful because you could put weight on the system which is not being used all of the time. So your battery actually could be worse off.
Okay, thank you.
That's just one. I mean, I don't work in the area. Okay, so just a very brief example that could be interesting to look at.
Okay.
What was the second question then?
The second question is, for the first question is whether you go for fixed split or dynamic split. The second one is, if you choose a split option, where to split exactly? Means if you have chosen any split, where you have taken, for what reason? Whether you have taken the bandwidth as a parameter, or latency as a parameter, or the energy consumption as a parameter.
So I mean, normally what it comes out is this. So anywhere you split between, at least within this, anywhere you split on the LLS, you will tend to have strict latency requirements. Okay, they might change a little bit, but not too much. Now CPRI is worse because there's also very strict synchronization requirements, which make the requirements worse. But latency-wise, these tend to be the same. So the only thing that changes is the capacity that you need of the fiber. So between here and here, the capacity requirement can change quite a bit.
Yes.
Now, where do you change? I mean, it's difficult to say. I know that. I mean, from let's say in the next few years, you likely only see one type of split, which is a 7.2, and that's because the industry really had to make a decision. What do we tell the vendors of remote units, of remote radio heads? Where do we tell them to split? Because they need to know. They need to build a piece of hardware. They need to know where to split. And there's been, considering a number of issues. One of important is the transmission capacity required, especially if you're using a passive optical network. They kind of decide that 7.2 seems to be quite a good split. If you split more, if you go higher, of course, your system is better in performance, but now your base station looks more and more like a normal base station. Okay, so the advantage of the low cost for the small cell, the more you go this way, the more you use the low cost advantage of your small cell, something that's small and so on. And the idea is that if you're using only a few watts of power, then it's nice because your small cell can actually be small, because the size of the small cell also depends on the power of your radio frequency. So if you look at 30 watt, you need something big. If you have something big, then adding a little bit of computation does not really change the size of the system. But if you have a small cell with 1 watt, that can be nice, small, and neat. If you start putting now a lot of computation, then you have to change the size of your base station. Well, I think there's also about how big is that system, and I think the 7.2 seems to be a good trade-off between keeping the cell small and low cost on one side and keeping the requirements of the requirements of the transmission not too bad. So that's my view, at least.
Okay, sir. I think it's time to conclude.